Now, last week was the Advances in Genome Biology and Technology meeting that I've organized now for 13 years down in Florida, which is really kind of the showcase for sequencing technology. And at that meeting, we had a late-breaking abstract provided by this company, Oxford Nanopore, on their Nanopore sequencing device that should, if it, again, is real, revolutionize everything that I've talked about today. We have to be skeptical, however, we are scientists. So this essentially could use two different processes for sequencing through nanopores. A not trivial technological feat, I might point out, that many have been pursuing at the academic level for well over 15 years now, with no tangible commercial success having resulted. So if these guys can do it, they're really bucking the trend, but we'll see. So there are two flavors, if you will, that are being proposed by this company. The one that wasn't talked about is this exonuclease-aided sequencing, where you can see a lipid bilayer here, a nanopore with a sensor of some sort, and an exonuclease poised right at the top, which would, of course, routinely and uniformly cleave off the DNA bases in this strand shown here, and electrical field would suck them through and detect them one at a time in a neat and orderly fashion. And if you can detect the sarcasm in my voice, you can imagine the ways in which that might go wrong. But that remains to be seen, because I don't think biology is always that neat and orderly for starters. But I am a skeptic, as you probably can tell by now. So the type of sequencing that was talked about as being sort of near-term, second half of 2012, a device would be available that looks, for all intents and purposes, like the data stick that I loaded my talk from today, is this pore translocation sequencing approach. Here you have a double-stranded molecule that's held by an enzyme, probably a helicase, that essentially single-strands it and preferentially feeds one strand down through the pore with a tether on this end to make it behave, because the biggest problem, or one of the biggest problems in nanopores, is that the DNA looks nice and straight in these beautiful pictures, but of course the tendency to form secondary structure or even base stacking interactions sometimes kiboshes the fact that it's actually going to go through that pore in a nice, orderly fashion. So these guys have apparently solved that problem. They're reporting base length reads of hundreds of thousands of bases, having sequenced through lambda in its entirety, for an example. All highly purified DNAs, I might add, and so it remains to be seen. And in their big version of this, which looks, you should check out their website if you're intrigued. It looks, for all intents and purposes, like a server rack in a data center. This would be the consumable that you would put into each one of those server modules, if you will, to perform large-scale sequencing. 2,000 to 8,000 nanopores per membrane that goes into this. You add on your DNA, you push the button, and you walk away. As it complexes it together with the enzyme, they find the nanopores, and the sequencing begins. I should point out that this is all detection by current fluctuation. So as the DNA translocates through the pore, the current fluctuation differs depending upon the triplet codon that's occupying that pore at the time. This group has studied that extensively for every triplet codon, and they have supposedly a hidden Markov model of what each triplet looks like, and you can infer the DNA-based sequence using that hidden Markov model base caller. Okay, so that's that. I'm going to spend just